Hey guys, having some technical problems here, and I had a recording and it simply didn't work. Sorry, I look all ruffled. I've been exercising. I actually exercise. It's hard to believe when you look at me. But hey, I want to do a lesson to real quick finish chapter 1 and get into the beginning of chapter 2. And so here we go. Let's get started. So first of all, the last slide in chapter 1. So here we go. Almost done with chapter 1. All this is review. Okay, and I know in period 4, I think you guys copied this down. So the states of matter, again, solid, liquid, gas, and we'll spend we're going to have a test on chapters 1 through 4, which is basically all review. Except for the second half of chapter 4, and that's going to be, again, a month or more. And then we'll do chapter 5, and chapter 5 is on gases, and we'll do review, and then we'll get into it. And then we'll do chapter 10, which, again, either right before or after the semester, probably into January, solids and liquids. But those are the states of matter, and we'll really go in depth on them. If I had a continuum where I had solids and gases, liquids would be much closer to a solid. There's 2 other states of matter. There is one that is a plasma. In period 4, we talked about this. And plasma is beyond a gas. It has more energy than a gas. And it's actually where the molecules, the nuclei and the electrons break apart. So it'd be like breaking apart of the atom. And there's also a 5th state of matter, which is before a solid. It's called Bose-Einstein condensate. And in that phase, and I think the only element that's ever been like that has been rubidium. And so Bose-Einstein condensate. So I always use the example, if we as a class could represent the molecules, if we were a gas in our classroom, each individual representing a gas molecule, we would be moving real fast and spread far apart. If we were a liquid, we would get much closer together and we would slide by each other. And if we were a solid, we would get even closer, and it's almost like we would just shake in place. Well, if we were a plasma, literally, we'd be moving really fast, we'd be far apart, and literally our arms would come off, we would start to break apart. And if we were Bose-Einstein condensate, we would all meld into one huge molecule, if that makes sense. So we'll go way more in depth on those. A mixture, 2 kinds of solids, homogeneous and heterogeneous. Homogeneous mixture is one that is the same throughout, and I'll give you an example. Tea with sugar dissolved in it. It could be milk, air, something that's consistent throughout. A heterogeneous mixture is one that is different throughout, like ice cubes. I've got there ice cubes and iced tea, Italian salad dressing, chocolate chip ice cream, raisin bran. Most of the things in the grocery store are going to be heterogeneous mixtures. Okay, and then physical change versus chemical change. And a physical change is a change of state of matter, melting ice. But in a physical change, you need to know you still have the same substance, it's just changed form. So melting ice, dissolving something in water, dissolving sugar in water. If you dissolve sugar in water, if you wanted to get those back, which in a physical change, you could get those back, you could evaporate the water and the sugar would come back. So any change of state, so melting, freezing, boiling, condensation, dissolving, all physical changes. You still have the same thing, they just changed form. Chemical change is a change where one substance into another, and this is a chemical reaction. So in a chemical change, something new is produced. Burning, cooking, rusting, these are always a chemical change. A chemical change is accompanied by a color change, a change in temperature, a change in state. Okay, so that concludes chapter 1, all review. Okay, now on to chapter 2. Okay, and here are the problems. And again, we'll be doing a lot of review here. So here are the problems, suggested problems for chapter 2. So by the time you guys come to class on the A's on Wednesday, the B's on Thursday. I would suggest that you guys have the chapter 1 problems due. And we'll get to a place here where it's a good place where you could be working in chapter 2. I'm going to give you, I'm hoping by the end of the week, we could be close to done with chapter 2. So you can note the problems. These are the suggested problems. Again, you'll never turn these in, but these are problems to, I would recommend I could put them on the test. Okay, this chapter, atoms, molecules, and ions. And this right here, just kind of some background. You don't need to remember this, but early history of chemistry, 400 BC, the Greeks thought that all matter was composed of 1 or 4 elements: earth, water, air, fire. And if I were in front of you, I would say, okay, how correct were they? Earth, water, air, fire, and they were wrong. But, and of course, if I were to ask you, if you would go back in your ancient history class, what were the Greeks known for? Well, they weren't known for science. They were known for philosophy. But they did have this. They also argued whether matter could be divided into infinitely smaller pieces or composed of small, indivisible particles, which they called atomos, later became atoms. So their contribution to the model was that the atom is something small and indivisible, or matter is made up of these small indivisible things called an atom, and that's where atomos comes from. And you can go to page 40 to 52, and you can go through all the progression. And real quick, the first person to come up with truly an empirical with some data on the atom was a guy named John Dalton, a British school teacher, and he looked at different compounds that consisted of the same elements, like CO and CO2, or H2O and H2O2. And he noticed that when you looked at them, that he law of multiple proportions, and he noticed that there was a ratio, and he came up with the idea that there's constant ratios in the matter. He came up with the idea of an atom, and he's still held to be the case 200 years later. Thomson was given credit for the discovery of the electron, and Rutherford was given credit for the discovery of the nucleus. Okay, and this is right out of our book. And the key things on this slide is the mass and the charge. And the thing you should note, if we took the mass of the proton, and notice those are negative exponents, so negative 27 is bigger than negative 31. So if I took 1.67 times 10 to the negative 27 divided by 9.11 times 10 to the negative 31, I think it's over 1,800 times. So two key things from this is that the mass of a proton and neutron are equal, and they are about 1,800, almost 2,000 times as heavy as an electron. Okay, so one key thing is mass. Is that an electron has a mass, but its mass is so small, it's ignored. Think if I gave one of you $1 and somebody else $1,800. Well, the one that got the $1,800 would be all happy, but the one that got one would think nothing. Well, that's the mass of an electron compared to a proton or neutron. It's worth ignoring. And then the charges. So first thing is mass, second thing is charge. So even though electrons don't weigh very much, their charge are equal and opposite that of protons. So electrons are -1, protons are +1, and neutrons are neutral. This thing on the bottom, this C down here, does not stand for degrees Celsius. It's a coulomb. And if we have time, depending, we're starting late and everything, that will be the last chapter we'll cover. We'll talk about that. It's a thing that has to do with electric charge, coulomb. Okay, and that you can't read, but it says the diameter of the nucleus is 10 to the -13th, and an electron cloud is 10 to the -8th. Again, negative exponents. So if I divided those, I would see the electron cloud is 10,000 times larger than the nucleus. Okay. Names of the elements. And in first year chem, you guys had a periodic table where you had the names of the elements right on the periodic table. And like the periodic table that I'm giving you guys on Monday and Tuesday, it's not like that. And that's the way it's going to be in AP Chem. Now, the periodic table that hangs on the wall in our classroom does have the names of the elements, but you're going to have to get those down. But what this table is showing is that some elements, their names and their symbols don't correspond, like the third one, iron. And when they do that, like a lot of the elements, symbols go right with their English names, like neon is Ne, oxygen is O, carbon is C, fluorine is F, argon is Ar, but not all of them. Iron is Fe, lead is Pb, mercury Hg, and so on. And the reason when there's not agreement like this, when the symbol and the name don't go together, they've used the Latin name to determine the symbol. So you can see iron is ferrum, kind of an interesting little background to lead. Lead was used in the Roman world, in the ancient world, for plumbing, and thus the name plumbum. One thing that the Romans didn't know, though, that if you're exposed to lead for too long, you get sick, and if you're exposed for a really long period of time, you could die. But that's where Pb for lead comes from. And there's silver, sodium, and sulfur, all is with an S. Silver, sodium, sulfur. Well, which one got the S as its symbol? The answer there is sulfur, and you can see silver is the Latin name argentum for Ag, and sodium, the Latin name natrium, Na. So I think just as we go through our class and what we had from first year chem, you will be familiar with the symbols and the names. Okay, isotopes. Well, you guys are copying this down. I'm going to go get my whiteboard real fast. Okay, I'm back with my whiteboard. I'm going to use this a little bit here. But an isotope is something we learned in first year chem. It's, and like it says at the top, the number of protons defines the type of element. So the number of protons is the atomic number, and the atomic number is the license plate of an element, and that's how you determine that. Well, an isotope is when you have two atoms with the same number of protons, so it's the same element, but they have a different number of neutrons. So an isotope, same element, different mass, because different number of neutrons. And you can see there sodium 23 and sodium 24. So, and it's already written out there, but if we've got, so I'm going to go back to the whiteboard here. Sorry for this way to do it, but like I said, I'm having technical problems trying to figure this thing out. Okay, so here I am. So if I have got, oh, my pen's not working. I go through all this. 23, 11. Hopefully you can see that. 23, 11. Pen isn't very good. Well, I do all this and it doesn't work. I'm just going to have to go back to the slide. Sorry about that. I thought I had my pen, but my pen isn't working. Technical problems for Mr. Wood on this one. It's a work in progress, guys. Okay, so back to this, but this will kind of show this, and I'll just talk you through this. Okay, so back to where we were. And so an isotope, same element, different mass. So in the upper left-hand corner, 23, that is the mass number. And the mass number is the protons plus the neutrons. The lower left-hand number is the atomic number, which, like I said, is the license plate of the element. And then Na is the symbol. And the symbol is connected to the atomic number. So in this, just like it says how many protons, if you look at the diagram, it tells you there's 11 protons and 12 neutrons. So in sodium 24, there's 13 neutrons and 11 protons. So the way you figure out the protons is based off the atomic number. The way you figure out the number of neutrons is you subtract mass number minus atomic numbers. So for 2311, that would be 23 minus 11 is 12. And for 2411, the one on the right, it'd be 24 minus 11. Okay, so the other way to write this isotope is like it says here, Na-23. So when it's written like that, the author, whoever wrote it, will assume that you can look up the atomic number of sodium as 11, and then they're telling you the mass number is 23. Okay, so then if we have this one, which is saying sodium 22, and it says how many protons and how many electrons is what this is saying. And so Na22 would mean the upper right-hand number is 22 and the lower number is 11. So the number of protons would be 11, and then the number of neutrons would be 22 minus 11, which is 11. You go, wait, they're equal. Well, sometimes they are equal and sometimes they are not. In this case, they are. Sometimes the protons and neutrons are equal. Okay, and you look on the bottom of this slide, 43, 45 through 48, and 51. These would be good problems to be working on now that we went over this. Okay, and this is where I want to just talk about it. This is where I'll pick up in class. But the next thing, and again, all this is review. So forces that hold atoms and molecules together as a bond. And before I put this up, I could ask you, do you remember the different kinds of bonding? And again, it's been a while now. But hopefully you can remember, we have covalent bonding, which is here. And then we have ionic bonding, which I'm going to talk about. So again, I didn't get quite as far as I wanted. I'm kind of still working through some technical problems, but this will be a good place to stop. And this is where we'll start in class. So what you guys can do is get these notes down. You guys can be working on the problems, finishing chapter 1, getting into chapter 2. And again, I'm going to give you a quiz. And we're going to do a lab. I don't know if we'll do it the first day or the second day of next week. So, hey, thanks for being patient with me, guys. And I will, let me see if I get out of this. Oh, gosh, I think I screwed it up. Okay, there we go. I think okay, sorry, but thanks, guys. And hey, I will look forward to seeing you guys in the next class. Bye.